Okay, before we really get very far into graphing of the toolkit functions, we want to talk about the arithmetic we need in order to do it. Okay, now I'm going to talk kind of briefly about it here, but there's going to be a longer video, a longer section on the stuff we got to know in order to do pre-calculus. Okay, the arithmetic and algebra operations that we need to understand a little better than most people understand them when they come into pre-calculus. Anyhow, what's division? Okay, division means how many of this would take to make that. Okay, let's see what that means. Well, how many twos does it take to make 10? Well, most people know that if you just divide 10 by 2, you get 5, and it takes 5 twos to make 10. More directly, and students are often discouraged from counting on their fingers. That's bull, okay, in my opinion. I counted my fingers, okay, and I was a top math student all the way through elementary, middle, and high school. Okay, so I counted my fingers. I learned numbers better than people who didn't, but people who just relied on memorization, which doesn't really connect you with the numbers. What do we mean by 10 divided by 2? Well, how many twos does it take to make 10? You can count it. 2, 4, 6, 8, 10. It's a handful, that's 5. It takes 5 twos to make 10. You got 1, 2, you got 2. You got 2 of them, you got 4. You got 3 of them, you got 8. If you got 4 of them, that gives you. Now, if you got 3 of them, you got 6. See, I'm good at arithmetic. Okay, 1 2 is 2. 2 twos is 4. 3 twos is 6. 4 twos is 8. 5 twos is 10. Okay, so I just proved it to myself. Hopefully I'm not losing track of that. Okay, so it takes 5. So that's the most visceral thing. It takes 5 twos to make 10. We can understand that completely. We could draw a number line from 0 to 10 and divide it into twos. Okay, it takes 5 twos to make 10. So we say that 10 divided by 2 equals 5. We could also say 10 divided by 2 equals 5 because 2 times 5 equals 10. Now, really, it's because 2, 4, 6, 8, 10. Okay, but in a more formal definition, we can say that one number divided by number. Okay, the quotient. This is the divisor. This is the quotient. Okay, this is called the dividend. If you multiply the divisor by the quotient, you have to get the dividend. Okay, so there we have it. Now, not going to worry about divisions that result in fractions, except for just simple reciprocals, because that's all we're going to need to do a toolkit function. Toolkit functions. So what I want to say is, though, that one thing you can't do so what's 10 divided by 0? Okay, well, a lot of people will say it's 0. I say no. it's not 0. If 10 divided by 0 is 0, then if we take this as our test, then 0 times 0 equals 10. Well, 0 times 0 doesn't equal 10. Zero times 0 is 0, not 10. So 10 over 0, and I want to use an emphatic word here. And this word is reserved by the world's greatest mathematicians for really strong emphasis. I'm going to say 10 over 0. I ain't 10. Ain't 0, it's not 10 either. I just kind of destroyed my emphasis there, but just saying it as strong as possible. And that's not really what world-class mathematicians do. But 10 over 0 is not 0. 10 over there, no number divided by 0 is 0. Now you could say, wait a minute, 0 divided by 0 is 0 because 0 times 0 equals 0. But there's a problem with that you don't really understand until you've done some limits in calculus. Okay, so even 0 okay, even 0 over 0 isn't 0 for other reasons. Okay, if this was your test and this is your only test, then you would have to say 0 over 0 is 0, but it's not so. Okay, some zeros are bigger than others. Yeah. I could explain that, but you don't want to do it. Okay, so there's division. This is what division means. And this is at least pretty complete explanation, except for 0 over 0 thing, of why no number divided by 0 is 0. We say that we can't define division by 0. We say it's undefined. Okay, now in doing some of the important toolkit functions, you're going to have the opportunity to divide by 0 because 0 is one of your standard values, and you're going to end up with a division by 0, and you're going to have to say, well, that's undefined, and 0 is then not part of the domain of our function. You might understand a little of that language, but we'll talk more about it. Okay, well, let's try another one. What's not 0? Now, if how many halves does it take to make 0? It doesn't take any. If you divide 0 by a number, you get 0, but if you divide by 0, you don't get an answer. Because we don't want to confuse those two things, but let's start. What is 1 divided by 1/2? First, how many 1/2 does it take to make 1? Well, obviously, it takes 2 halves to make 1. So 1 divided by 1/2 has to equal 2. Now, is this consistent with what we said before? 1 divided by 1/2 equals 2 means that it takes 2 1/2 to make 1, right? This is consistent with what we said before. If you multiply the divisor by the quotient, you get the dividend. In other words, 1 over 1/2 is 2 because it takes 2 1/2 to make 1. This is how you write it with numerical calculations. Okay. Now, the general rule. If you divide 1 by a fraction, call the fraction P over Q. You could write that as 1 divided by P over Q. Then you get 1 times Q over P, which just equals Q over P. Now, if it's not 1 here, if it was like 12, then you'd have 12 divided by P over Q is 12 times Q over P. That'd be 12 Q over P. So I could write that out in symbols, but I don't want to get too heavy in symbols right now. General rule is you take the denominator and flip it over and multiply. Okay, that's a rule that you learned in 5th grade. You probably did it right in 5th grade. You wouldn't have passed math in 5th grade, I hope. And I hope you did pass math in 5th grade. You wouldn't have passed math in 5th grade if you hadn't known how to do this. Yeah, that's probably stuff. At that point, you've overused calculators, and your school's allowed you to overuse calculators in the meantime, and you might have forgotten some of these rules. Okay, so that's why we're reviewing. Okay, well, so far, I mean, that's enough about division, even a little more than you really need at this point. Make sure you understand this much, and then that should carry you through any of the division you need to do with the toolkit functions. Okay, your rules for exponents are kind of confusing. Okay, you have the rule that says x to the a times x to the b equals x to the a plus b. And that's the rule that's most important right now for evaluating the toolkit functions, some of the toolkit functions at the standard values. So that's the one we're going to concentrate on. We'll say more about exponents later. It's real easy to confuse this x to the a raised to the b, in which case you would have an exponent that's a times b. You're multiplying, it looks like you ought to do a times b up here, but no, it's a plus b. And it's real easy to see why. Example. What's x squared times x cubed? Well, I'll prove to you that it has to be x to the 5th, not x to the 6th. When you multiply the exponents, you get x to the 6th, but you add the exponents. Why is this? X squared means x times x. And x cubed means x times x times x. And that equals well, we don't need parentheses, we just write it this way. That's x to the 5th. X squared is a string of 2 x's, x cubed is a string of 3 x's. If you multiply a string of 2 x's by a string of 3 x's, you get 5 x's, which is x to the 5th. You get a string of 5 x's. Okay, so that should satisfy Okay, now. What then is x to the third multiplied by x to the negative third? Now you don't know, probably don't remember what x to the negative third means. The majority, many of you will, but a strong majority of students coming into pre-calculus don't remember what a negative exponent does. Okay. One thing we can say is that x to the third times x to the negative third has to equal x to the 3 plus negative 3. If this is going to be our rule, and it has to be because of what I just showed you, then it has to apply even if you have negative exponents. If we want to have a consistent mathematical notation, it has to be this way. What's x to the third plus negative 3? That's x to the 0. Now, I hope you understand that x to the 0 equals 1. So that x to the third times x to the negative 3 is equal to 1. Well, if I divide both sides here by x to the third, x to the negative third has to equal 1 divided by x to the third. So general rule, x to the negative a is the reciprocal of x to the a. So that's one of your rules of exponents. Now, let's think about why we would want to say x to the 0 equals 1. And let me do this with some numbers. Okay, let's take powers of 2. Okay. 2 to the third is 8. 2 times 2 is 4 times 2 is 8. 2 to the second is 4. 2 to the first is 2. Let's just look at the pattern here. What's the pattern? 8, 4, 2, without even thinking about the fact that this is 2 to the third, 2 to the second, 2 to the first. What's the pattern? This is half of this, and this is half of this, right? Okay. And each power over here is 1 less than the one above it. So our pattern becomes pretty clear. We got the third power, the second power, the first power. What's going to be next? 3, 2, 1, blasting off a rocket, 0. So we're going to get 2 to the 0. If we continue, we go into the negative numbers. But right here is a list of powers of 2, from 3 down to negative 3, going down by 1 each time. Now, if we take the first 3 powers, we have the pattern that each number is half the one above it. And well, then this power should be half the number above it. Half of 2 is 1. Half of 1 is 1/2. Half of 1/2 is 1/4. Half of 1/4 is 1/8. And remember, if we start with let's just say we start with 1, Here's 1/2, halfway to 0 is 1/4, halfway to 0 is 1/8, halfway to 0 is 1/16. We saw that with the first numerical exercise we did with the scaling of an interval. We're scaling the interval from A to B, and A is 0 and B is 1. This is what we get. We got it before. We should recognize it. Okay. If this is 2 to the 0, this is 2 to the -1. This is 2 to the -2nd. And here's 2 to the -3rd. And there's even 2 to the -4th. So this pattern should be convincing about why we say that a number to the 0 power is 1. We don't have to use 2, but we see it worked if 2 was our number. Okay, 2 to the 0 has to equal 1. If we want to know what 3 to the 0 is, well, 3 to the 3rd is 27, 3 squared is 9, 3 to the 1st is 3. So 3 to the 0, what? Each of these numbers is a third of the one above it. 3 to 0 is going to have to be 1. And then 3 to the -1 is going to have to be 1/3. We see we even get the pattern for our negative exponents, because the negative exponents here all obey the same rule that we wrote over here. X to the -a is 1/x². 2 to the -3 is 1/2 to the 3rd, which is 1/8. There it is. Okay, so all this is very consistent. So we have to understand this much about exponents to get the clear, visceral, gut level, means the same thing as visceral, understanding of some of our basic toolkit graphs. Okay, now we're going to want to construct a graph with a toolkit exponential function. I'm not going to do that here, but that one actually turns out, once you get the rules down and get the table right, to be the easiest one to graph. Okay, but it's also, well, the squaring function and the basic exponential for toolkit exponential function, I would consider the two most important. Okay, now there's a problem with this. Or half is a standard value. Can you calculate 2 to the 1/2 power? Well, you should be familiar, might not be, but you should be. Two to the 1/2 is the square root of 2. Okay, and we can approximate that. But this isn't exact. Okay. How could we calculate the exact value of 2 to the 1/2? Turns out we can't. There is an exact value. We can prove that. It's much higher past, it's upper division undergraduate course where you would actually prove that. But we can't calculate it. Neither can your calculator. Their calculators give you 1.414, and they give you about half a dozen more numbers out there, but it's still not exact. And you can never write it down exactly. You can never locate it exactly on the number line. Okay. We're going to say, when we get something we can't calculate exactly, we're not going to use it. Okay. You won't use it. We would make our table for y equals 2 to the x. Fortunately, we won't need it. Let me just give you an example of how you might calculate the 1/2 power of a number. The easiest number to calculate the 1/2 power of is E. Now, E stands for the limiting value as n goes to infinity of 1 plus 1 over n raised to the n power. You can take your calculator. Yeah, we're not using a calculator to do these basic functions. You can take a calculator and see that n never stops. N approaches infinity, means you got to keep going and it can never stop and you're never there. Can't ever get there. Okay, if you let n equal 1, this is 1 plus 1 to the 1. Well, that's 2 to the 1 power, that's 2. If you let n equal 2, it's 1 plus 1/2 to the second power. Well, that's 1.5 squared, which is 2.25. Now, that's just for n equals 1 and 2. If you get out to n equals 100 or so, he's going to be approximately 2.7182. Okay. You're still not there. Never will be. But here's a scheme for calculating e to the 1/2. But let's just say calculating e to the x. It's 1 plus x squared over 2 times 1. And let's write things. X over 1 plus x squared over 2 times 1 plus x cubed over 3 times 2 times 1 plus x to the 4th over 4 times 3 times 2 times 1. And it just keeps going. Now, these are all numbers we can calculate. You know, you don't get too far before you get to numbers you really don't want to have to calculate. Still, all these numbers have values that can be calculated for at least a lot of the values of x. So that e to the 1/2 let's do 1/2 for x, and then just start calculating. Let me know when you're done. Well, you're never done. It's never finished. Okay. Since you don't want to have to do this, I'm going to disallow it from the basic table of the standard value table of the basic toolkit exponential function. Okay. So just a couple of things. So when we get to that, you have some understanding of why you really don't want to go there. And again, we're not going to allow it because it takes a calculator. It doesn't take a calculator to do any of the other calculations. All the calculations you can do for the basic toolkit functions are either calculations that you can't even in principle get an exact value for, or the ones where the calculation is simply undefined. Okay, so let's go on and make a couple of tables.